All right, we are ready to go. So what we're going to be doing today is we're going to continue our look at sampling methods, and we are going to briefly wrap up what we started last time when we first took a look at how samples can be selected and some of the good ways and some of the not so good ways of doing that. And then we'll take a look at some of the techniques that statisticians have developed in order to make samples possible in the real world. Because as we're going to see, the ideal sample technique is not often feasible, but we have to operate in the real world. So we'll take a look at those techniques that are used. And then finally, we're going to end today's meeting with a look at inference scope to make sure that when we make inferences from a sample to a population, we're doing it in an intelligent way, while at the same time not ignoring possible implications. And you'll see exactly what I mean when we get to that part. So today, once again, we are going to be taking a look at the idea of taking a sample from a population, trying to infer something about the population. And as we've seen last time, when you can take samples multiple times, you oftentimes end up with different averages for that sample, different samples that you've selected. And that really is what you can think of as happening in all these different multiple Earths. And we need to know, how does our Earth stack up against the multiple Earths? And that's one of the things that sampling allows us to do. However, we are also going to start taking a look at certain techniques that also allow us to basically take a whole bunch of data and describe it in a very succinct way. So this is the other side of statistics. This is descriptive statistics, which basically allows you to do an elevator pitch of the important ideas that your data represents. So it's almost like coming up with an elevator pitch. If somebody asks you, hey, what is it that you do at IUSB? If somebody asks you, hey, what is it that, you have this new project, what's it all about? You want to make sure that you have that ability to do a very short but succinct, true statement of that. All right, and that's what we're going to start diving into in the coming weeks as well. We start taking a look at, if somebody asked you, or if somebody asked me, for example, hey, how's your statistics class doing? I wouldn't tell them, oh, well, I have one student that has an A+, I have another student that has an A+, I have one student that has a B, I have another student that has an A-. That's too much. What they want to know is, hey, on average, how is your class doing? So we're going to start delving into those things as well, so that we can take a whole bunch of data from a very large sample and condense it down into something that our human minds can understand. All right, so today we are going to revisit one thing that we did previously, which is the Federalist Papers example, and I will hopefully do a better job of driving home the point that we were trying to make last time. And then we're going to take a look at sampling method basics, just a sort of brief introduction. And then we're going to go into a deeper dive into some of the specific techniques of sampling, such as simple random sampling, stratified random sampling. We'll do a demonstration with sampling sunflowers, and then cluster random sampling and systematic random sampling. And then finally, we're going to take a look at scope of inference, take a look at an example where it was done incredibly poorly, but then also take a look at an example where it was done extremely well. And spoiler alert, both of these use samples of animal subjects. So we'll see what the difference is between doing inference well and doing inference very poorly. But first, we got to wind back that clock. We got to go to our example that we did in our last meeting, and that is the Federalist Papers demo. And this is just going to be a wrap up of that demo. So what we were trying to do in this demonstration, when you boil it down to the basics of what we were doing, we had this paragraph here. And this paragraph, for our purposes, represents the population of words that we are interested in, right? So we want to know, what is the average length of this population of words, these 130 words that are in this paragraph. But rather than going through all 130 of those, we chose samples. And we did it randomly, where we just randomly by our own, well, actually not randomly, we did it on our own using our own human minds to just choose 5 words, count up the word length, and then discover the average of that sample of words in the hopes that we would have a good estimate for what the actual average length was in the entire paragraph. So you might remember this Excel sheet here. So when we did that exercise and we polled the classroom, these were the self-selected averages that we came up with. So those were the values that when people chose words on their own, just said, hey, I'm going to choose words out of this, and this one looks good, and I'll take this one, and I'll take this one. We ended up with these averages for the average length of a sample of 5 words. When I used Excel to create a random sample of those words, these are the lengths that we ended up when we used a random sampling of 5 words from those 130 words in that paragraph. All right. And then this is what I don't think I did a good job driving home, so we're just going to try it one more time. So here we're going to visualize that data. So there's a lot of insight that can be gleaned from this data and this data here. But this is not an elevator pitch right now. This is very complicated. This is something that our human minds just can't understand. If I asked you, well, which one of these is more accurate? Which one of these gave us a better estimate? It's really hard to take a look at that data and say, oh, it's the self-selected samples or it's the random samples. So what we need to do is we need to find a way to elevator pitch this. We need to find a way to represent it. And we're going to do it here in what is known as a histogram. So what we have here on the x-axis is we have the word length average. So each sample was rounded to the nearest whole word length. So did you find a word length average that was 5? Did you find a word length average that was 8? That's where it's going to show up on the x-axis, which is word length average. And then on the y-axis, we have the frequency. So out of the, I believe the 12 responses that we had, how often was an average of 5 in the sample? How often did a sample give you an average of 6? How often did 7 occur? How often did 9 occur? The higher the line, the greater the frequency, and that's on that y-axis there. So what we want is we want to discover what is the actual average of those 130 words. And if you went and you calculated that for all 130 words, you would find out that the actual true average is 4.9 words. That is what you would get if you took all 130. You took the entire population of words that we're interested in, and you did that calculation. But that would have taken us the entire class. So what we did is we did something that was more feasible, and we started sampling. When you did a self-selected sample, this was the distribution of averages that we received. So we had absolutely nobody finding an average of 1. We had absolutely nobody finding an average of average word length of 2. No one found an average word length of 3. No one found an average word length of 4. One student found an average word length of 5. 4 students found an average word length of 6. 3 students found an average word length of 7. Nobody found an average word length of 8 or 9, and 1 student found an average word length of 10. So that's a nice visual representation that lets you know how those averages were distributed amongst the multiple averages that we selected. The big problem here is that when you're taking samples, you want your sample to predict the actual true average in a non-biased way. And what we have here is we have bias. So you can see that the center of mass of this distribution, most of this distribution, however you want to think about it, the bulk of this distribution is larger than the actual true average. That means that it's biased. It's biased to overestimate how long the words actually are. So though your self-selected samples, because of the way that our minds work, tend to choose longer words than are actually in the paragraph, and our samples tend to have longer average word length. On the other hand, if you do the same analysis, but you use randomization, random number generator, to decide which words get selected, this is your distribution. Now you can see that in the same way as this distribution, there are a lot of samples that are off, right? So 6 times we underestimated with an average of 4. 3 times we overestimated with an average of 6. 1 time we overestimated with an average word length of 7. 2 times we overestimated with an average word length of 8. However, this is a better strategy because this distribution is not biased. This distribution is centered on the actual true value. So sometimes you'll overestimate, sometimes you'll underestimate. That's just sampling error. But in general, you're hitting that center. You're hitting the actual true value in a way that we didn't when we were self-selecting our samples. Now, the last thing that I want to say about this is I never want to give the impression, and oftentimes this happens, that our minds suck at certain things. So I remember when I first revealed this last class, I saw some looks on faces when we saw that we overestimated when we self-selected our sample, and everybody looked a little bit disappointed. Like somehow they failed some sort of life test. I just want you to know that your mind is set up to be maximally effective with minimum resources and effort. So it's trying to get the most out of doing the least. And that's really an efficient strategy to use. And if you take a look at your survival and human survival through eons, we were not made to notice average things. We were not made to notice mundane things. So fruit on a tree, red fruit on a green tree, that red fruit is not average. And we are programmed to notice that so that we can find food. A saber-toothed tiger that's 20 feet from you is not average, right? That's not an average occurrence. So we're made to notice the things that are most important or the things that are most striking or the things that are the least average. That's great for survival, and our minds should do that. However, it's not good for statistics. So this is one of the reasons why I think statistics took forever to develop as a mathematics, as an approach to understanding the world. We had geometry, we had calculus, we had all these other things before it, because your mind is just not made to think like a statistician. So that's fine. You're going to see many times in this course that you think that something is true and statistics tells you, no, it's not true. Or you think something's untrue and statistics will tell you, yes, it actually is true. That's why we have statistics, because we just can't, we're not built to do it on our own. All right. So that's our lead in to what we're going to be doing today, which is taking a look at sampling methods. And again, sampling, just like if you go to a store and you want to know if the population of almonds is good, you don't eat the whole tray. You just take 1 or 2 to decide if it's good. So we need a way to do that and apply it to the actual real world and apply it to ideas that we have and things that we want to test in psychology. So let's take a look at some sampling basics, and we're going to split this up right off the bat into poor sampling techniques and proper sampling techniques. So these you can think of as kind of goals to avoid poor sampling methods and to attain proper sampling methods, with the realization that you're probably never going to do it perfectly. And that is one of the reasons why it's very important to know how a sample is collected, because there are certain pros and cons in doing it one way versus doing it another. So for example, poor sampling methods. One poor sampling method is called a convenience sample. And a convenience sample consists of a sample taken from a population, but only of individuals who are easy to reach. So it's right there in the name. These are not people chosen at random. These are people chosen because they're convenient. So if I was doing a study on perception of images and I just said, hey, everybody in this room, you guys are all in the study, you're a sample, but you're a convenient sample because everybody's here, you're readily available. That is a poor sampling technique. Another poor sampling technique is the voluntary response sample. And a voluntary response sample consists of people who choose to be in a sample by responding to some general invitation. So they are not selected to be in the sample and then contacted. On the other hand, everybody is contacted, and it's just whoever responds ends up being in the sample. So we have two poor sampling methods, one convenience sample, individuals in the population who are easy to reach, two voluntary response sample, people who are chosen to be in the sample by responding to a general invitation. And if you're thinking about your experience in Introduction to Psychology, if you're thinking about your opportunities to serve in psychology experiments for extra credit while you were in psychology, you will notice that you, as a psychology subject, as a university subject, is actually a convenience sample because they're readily available for professors, and they're voluntary sampling because professors will ask the entire class. They'll say, hey, we got extra bonus points available, and it's only those who choose to respond to the invitation that end up in the study. So you can see that using university students is on the poor side of sampling techniques, both for convenience sampling and for voluntary sampling, especially if you are going to apply it to the general population. And this is something that, again, you want to be aware of because historically, 70 to 80% of all psychology studies used university students. So if you go back to the early 2000s and earlier than, and any study that's earlier than that, 70 to 80% of those studies were convenience sampled, invitation sampled university students. So the bulk of psychology findings were done with these samples that did not use the best sampling techniques. In 2008, a study by Arnett found that about approximately 80% of samples in APA published studies consisted of samples of undergraduate psychology students. That is actually going down these days because now it's closer to about 25% because online samples have now increased in their use in psychology. So this is actual footage of a student doing one of my experiments online. And so anyways, online samples have started to increase. And these ones are not convenient samples anymore because it's not that we're conveniently only asking people who we have access to. However, they are definitely voluntary response because if you use things like Amazon's Mechanical Turk to get your subjects, it's only people that agree to do your study that you're actually going to be able to use, people that accept your general invitation. All right, enough of him. So those are poor sampling methods. And I just want to say one more time, they're not useless sampling methods. It's not like we should ignore 80% of psychology because it was done with convenience sampling and voluntary response sampling. But it is something to keep in mind, especially when you're interpreting results, to think about how is this sample done? How is it collected? Is it university students? And then if I'm trying to, and we'll get to this later, if I'm trying to infer from that sample, how far can I infer? What population can I infer this to in terms of taking it from your sample to general population conclusions? All right, so what's the proper sampling method? The most basic principle to have a proper sample is having a random sample. And what a random sample means is that your sample consists of individuals from the population that you are interested in. And they are selected for this sample using a completely chance process. So let's say that I was interested in doing a study and it was on development. It was a neuropsychology study on the development of the frontal lobe. So I wanted people that were between the ages of 25 to 30. If I did an actual random sample, that means that any person in existence that is between the ages of 25 and 30 has an equal chance of participating in my study. That's kind of the goal, but that would mean that not only are 25 to 30-year-olds in this class right now eligible for my study, but also 25 to 30-year-olds anywhere in Indiana are eligible. 25 to 30-year-olds anywhere in the United States are eligible. 25 to 30-year-olds anywhere in the world are eligible. So I might pick somebody at random out of the population, and they might be in Australia, or they might be in India, or they might be in China. All of those are equally likely to be chosen in a random sample. So you can imagine that this is very, very, very rarely done, and just not something that typically occurs when you're doing a study. So if you are doing random samples, it can oftentimes, or sorry, not if you're doing a random sample, but if you're doing sampling just in general, one thing that can often occur is a thing called undercoverage. And undercoverage occurs when some members of the population, they're less likely to be chosen or cannot be chosen for the sample. So maybe I can't recruit people from Australia. Maybe I'm not allowed to recruit people from China. Maybe they are just massively less likely to respond to an email from somebody from the Indiana University South Bend. All of this can lead to undercoverage. And this is actually something that came to people's attention in around 2010 with a study by Heinrich Hein and Norenzayan. And they coined the term, I believe they coined it, but it's called weird. And this is known as the weird critique. And they showed that 96% of samples in top journals in the 2000s were from what they called weird populations. And weird stood for Western, educated, industrialized, rich, and democratic. So countries that were Western, people that were highly educated, countries that were industrialized, areas that were rich, and places that were democratic, that was 95% of your samples in the 2000s. So that is an example of undercoverage, because people in Eastern countries are much less likely to be chosen or much less likely to be included in that sample. People who are not educated, less likely to be chosen. People from rural areas, not industrialized, less likely to be chosen. People who aren't rich in their socioeconomic status, less likely to be chosen. And countries that don't have democratic governments, far less to be likely to be chosen. So it's important to, again, realize these, because we are going to try to generalize from a sample to a population. So it's important to know where your sample came from so that you can generalize intelligently. All right, any questions on those sampling method basics? All right, so that was the basics. Now we're going to take a little bit of a deeper dive into sampling. So we're going to take a look at a few techniques that are made to feasibly do samples while at the same time acknowledging the difficulty in just randomly choosing anybody from anywhere in the world. So the first one we're going to talk about is randomly choosing anybody from anywhere in the world. So we'll just start with this as a point of comparison. So this is called the simple random sample, or an SRS. Never call it an SRS. If you see the word SRS, say it in your mind, simple random sample. So this is a simple random sample, and it can be achieved in one step. Step one, randomly select n individuals from the population. The symbol n, or the term n, that is a variable. That is a special variable in statistics. It is reserved for the size of a sample. So when you see n individuals, that means randomly select a sample of size n from the population. So if n equals 4, this means randomly select 4 individuals from the population. So again, if I was doing a study and I wanted a sample of 4 adults that were between the ages of 25 and 30 years old, I would just start pulling random individuals out of the population. I would use a random number generator to pull 4 people out of the population. And again, simple random sample is the entire population of 25 to 30-year-olds. So I might randomly select this individual here, and they are now going to be invited to be in the study. I might randomly select this individual here, select this individual here, and we select this individual here. They are all equally as likely to be selected for this study. Now, some of these might decide to participate. One of them is probably not going to. And this is a phenomenon known as non-response. So non-response occurs when an individual that is from the sample either can't be contacted or refuses to participate. So we're probably going to lose one of these individuals. But that is your simple random sample. Anybody in the world that fits your population, that is in your population, whatever constraints you put on that population, for example, 25 to 30 years old, everybody is eligible. And you just randomly pick from that population, that's your simple random sample. So, as you can imagine, simple random samples almost never happen. So what are the alternatives? What can we actually do in the real world to intelligently sample and not try to invite A-list celebrities to participate in your study? So one alternative that we have is stratified random sampling. So in stratified random sampling, there are 3 steps. Step number 1 is you determine a strata. And what a strata is, it is groups of individuals that have a particular characteristic. They share a particular characteristic. And importantly, that characteristic is thought to be associated with the variable that you're measuring in a study. So you're interested in a particular variable, but there's another variable, there's another characteristic that you think might influence the variable that you're measuring. So you make these strata based on that characteristic. I'm going to set this up. This will make more sense when we get to the example. So that was step 1. Step 2, you do a simple random sample in each strata. So you have your strata, and then you do a simple random sample in each of those. And then step 3, every selected individual from each strata goes into your sample. So you, on step 3, just combine everybody into your final sample that you use for your experiment. So how would that work? Well, let's say that I was doing a study on memory. I wanted to do a study on memory, and I thought to myself, all right, I have my variable. My variable is memory. Some people are going to do great on my memory test. Some people are going to do not so great on my memory test. That's my variable. That's what I want to measure. My study is on memory. But I want to be able to apply this to the general population. And one characteristic that the research indicates that might be associated with my variable of memory that I'm measuring is age. So research might suggest that as you get older, your memory changes. There's certain decreases in your ability to remember things. There's certain increases in your ability to remember other things. It changes as you age. So I might say to myself, hey, I'm interested in memory, but age is a characteristic thought to be associated with that memory variable. So I'm going to split my population into strata before I do my random sample. So what I would do is I would say, all right, I'm going to split this population into 5 strata. I got strata number 1, that's going to be children. So strata number 1 is the population, but only the children. Strata number 2, those are teens. Strata number 3, those are emerging adults. Strata number 4, midlife adults. And then strata number 5, older adults. And what I'm going to do is I'm going to split them up into that strata, and then I'm going to say, all right, I'm going to do a simple random sample in strata number 1. So I'm just going to be selecting from children, and I'm going to randomly select, for example, 10 subjects from the children's strata. Then I go to the teen strata, and I say, let me randomly select 10 from there. Then I go to the emerging adult strata, and I randomly select 10 from there. And I do that for the midlife strata. I do that for the older adult strata. And then I combine all of those into a sample of 50. and that is stratified random sampling. So that is a really powerful way to get a good estimate of a population when a characteristic can affect your variable. And to kind of illustrate that, we are going to do a demonstration right now, and it is the sunflower demonstration. So I'm going to read the description first, and then we'll switch over to the demo. So a British farmer grows sunflowers for making sunflower oil. Her field is arranged in a grid pattern with 10 rows and 10 columns as shown in the figures below. Oops. Those figures below. All right, so this is her field over here. And her field is a square field, and it's got 10 rows, and it's got 10 columns, and that's how she divides up her field. The farmer would like to estimate the number of healthy plants in the field so she can project how much money she'll make from selling them. It would take too much time to count the plants in all 100 squares, so she'll accept an estimate based on a sample of 10 squares. So it would take way too long to count up all the plants in all the squares. So she says, well, you know what, I'm just going to count how many healthy plants there are in a sample of 10 squares out of the 100. Which sampling method will give her the best estimate? So we're going to go through 3 different sampling methods. And the first one we're going to do is a simple random sample of 10 squares. So we're going to do a simple random sample of 10 squares here. I'm going to hit generate sample. And then what this does is it basically puts X's in the plots that were chosen as part of the sample. So the farmer would go here and she would count the number of healthy plants in this little plot here. She would count the number of healthy plants in this little section here, count the number of healthy plants in this section here. And you can see that it's kind of spread out randomly amongst all of the area. So the next one down is stratified by row. Now, why might you stratify by row? Why might you create strata that are split by row? The reason is because you think that there is some other characteristic that might affect rows in terms of their location on the grid. So can anybody think of something that might affect that? Hint, I mentioned the irrigation ditches. All right, so I'm not a farmer either. I didn't get this when I was trying to do this for the first time. But here's an irrigation ditch. So this is water over here. And this is water over here. And you might say to yourself, hey, I'm not a farmer or anything, but I think plants need water to live. So maybe the plants that are closer are going to be in general healthier. Now, I want an estimate of the entire field here, but I think that closeness to the water is going to be a characteristic that might affect my variable, the health of the plants. So what I'm going to want to do is I'm going to want to stratify by row. I'm going to want to make sure that we only get one selection from each of these rows. So we generate a sample, and you can see here that it's randomly distributed again. But we have one sample in the first row, the top one here. We got one sample, one plot chosen from the second row, one plot chosen from the third row, one from the fourth. We have one chosen from every single row. We're missing some columns. You'll notice that there are no plots selected in the first column. There are no plots selected in the 8th column over here. So we're missing some columns because we stratified by row. So we randomly selected 1 out of 10 areas in the first row. We randomly selected 1 out of 10 areas in the 7th row. We randomly selected 1 out of the 10 areas in each row, and then we collect those all into a final sample. And then the last one that we have here, and this is why you don't just stratify without a plan or without a theory, stratify by column. So let's say that we didn't identify a characteristic that contributes to the health of the plants, and we decide to stratify by column. instead of stratifying by row. So once again, we can generate that sample. And you can see now that in every single one of these columns, one area is selected for our sample. So we got one area in column 3 here, one area in column 4, one area in column 5. And this time, some rows are ignored. So rows 3 and 4, there weren't any plots selected from rows 3 and 4. So those are 3 different ways that we could do samples from this plot. So now let's actually reveal the results. So if we actually had the manpower to go out and measure every single plant and every single plot and count up how many healthy plants there were, this is what we would find. So this plot over here, this first one here, that had 106 healthy plants. This plot over here, it only had 98 healthy plants. This one over here had 101. This one over here had 107. So basically there's 10,000 plants approximate that she's counting up. That's a lot of plants to count. So the true mean of the healthy plants is 1.2. Now let's go back up here and see how our samples did. So here we have the actual true mean. This is what we're trying to get to. And we can see that we've overestimated it with our simple random sample, just choosing 10 out of the 100. Doesn't matter what row, doesn't matter what column, just choosing 10 out of the 100. We end up with 103. Not too bad. The actual mean is 102. We're not that far off. For here, for the stratified by row, we actually end up with 102.6, a little bit closer than the previous one to that true mean. And then we have this one down here, and this one down here is pretty far off at 103.1. However, this is only one sample for each of these. And what we can do with our power to look into the multiverse is to say, hey, if this farmer existed on an alternative Earth and they took a sample, where might their samples occur? What average might they get? And we can do that by generating a new sample here, and it'll plot it over here. So we can see now that on an alternative Earth, not her Earth, the farmer got an average of 103.3. And we can do that again. And we can do it again and again. And we can keep doing it, and it just rescaled a little bit. That's why the true mean moved over. And we can keep doing it. And I'm just going to fill this up a little bit. So each of those is a farmer in an alternative Earth doing this stratified random sample and getting a result. And as you can see, this stratified random sample, sampling randomly, has given us an unbiased estimator for the population of plants. Because you can see here now that we have some samples that overestimate the true mean. We have some samples that underestimate the true mean. But unlike our example in the Federalist Papers, it's balanced on both sides. There's no general bias. It's not biased in one direction or another. So even though we have a pretty wide spread, it's doing a good job of being a non-biased estimator. And that's one of the reasons why we use random sampling, because random sampling leads to non-biased estimations of the population. All right, so that was a simple random sample. What about stratifying by row? So when we stratified by row, remember that what we did is we said, hey, we think row is important. Distance from the irrigation ditch might be important. It might be a characteristic that is associated with plant health. So let's stratify by row, and we'll now see how well that does at estimating what the true mean is. So we'll generate a new sample, again, another alternate Earth, and that farmer got 102.4 instead of 102.6. We'll generate a new sample. That farmer got 102. And we can keep generating new samples, keep generating new alternative Earths, and we'll do that over and over again. And the first thing you'll start to notice is that this stratified sampling by row is also a non-biased estimator. So we have a bunch of them that are overestimating what the actual true mean is. We got a bunch of them that are underestimating what the actual true mean is, but they're doing a pretty good job of being non-biased. However, the big important thing to see is that this spread here is way smaller than this spread here. So when we stratify by row, and row is associated with the variable that we're trying to measure, we get a much tighter spread on our sample, which means that we reduce sampling error than we do if we just chose a random sample. So both of these are non-biased. Both of these can be used as a non-biased estimator, but random sampling gives you a wide spread. So you take your risk. Maybe you're really far off on the plus side. Maybe you're really far off on the bottom side. But when you stratify by a characteristic that is associated with your variable, you get a much tighter spread, so you have much less sampling error. And it's not just the stratification that does it, because when you stratify by column is not associated with the actual health of the plant because it's not associated with the distance from the irrigation ditches. So here you can see that once again, we have a really wide spread, non-biased estimator, still centered around that true mean, but way more sampling error than you would get with a method where you stratify by rows. So stratified random sampling gives you a good way of maximizing the power of your sample because it gives you a tighter distribution and you're more likely to be close to that true mean, which is what we're trying to predict. Any questions on this demo before we head up to the next strategy? Yeah, just a few more. All right. Okay, so that was stratified random sampling. The next technique that we're going to take a look at is called cluster random sampling. And this one is also a multiple step technique. And the first thing that you do is you identify clusters. So in stratified random sampling, you determine your strata. In cluster random sampling, you identify clusters. And what a cluster is it's a group of individuals in the population that are located near each other. So they're just clustered together, right? They're in a certain town, or they're in a certain postal code, or they live in the same housing district, right? So they're located near each other. That's what a cluster is. So you take your population and you identify clusters in your population. Then what you do is you do a simple random sample, not of the people, but of the clusters. So step 2 is to do a simple random sample of the clusters. So you might have 100 different postal codes, and you say, I'm going to randomly choose 10 of those postal codes. And that's going to be the random sampling that I do of the clusters. So it's not of the people yet, it's of the clusters. And then what you do in step 3 to actually get your individuals is that each individual from that selected cluster goes into the sample. So if you chose a particular postal code for your in your cluster, everybody in that postal code gets invited to be part of the sample. Everybody in that cluster goes into your sample. Now, of course, you're going to get non-responses in that strategy. You're going to get that in all types of sampling. This one probably more than others, but that's the way that it's done. You identify your clusters. You do a simple random sampling of the clusters. So you don't choose all your clusters. You just choose a sample of the clusters. And then everybody that's in that cluster goes into your sample. So this is something that is oftentimes used when you're doing a study on a population that is really large and they're spread out over a wide area. So if you ever want to know something about the population of a country, typically you would use a strategy like clustered random sampling. So one example that recently came out was the British National Survey of Sexual Attitudes and Lifestyles. So this was the NatSal 3. So this British National Survey, this is a large population. So they want to know about the entire British population, spread out over a large area, spread out over all of England. So this was a perfect situation to use clustered random sampling. And one of the things that we'll see in just a moment is going to be delayed for just a moment. All right, so not to muddy the waters, let's talk about clustered random sampling. What they did in this study is they used a multi-stage, clustered and stratified, we'll get to that, probability sample design with postcode sectors selected as the primary sampling units. So in this study, what they did is they said, all right, we are going to take all the postcodes, all the postal codes, we call them postal codes, all the postal codes in England, and we are going to randomly select from those postal codes. So they'll take all the codes that they have, and then they just randomly select from those codes. And then anybody in that code that gets randomly selected, all of them are sent out the census. All of them are included in the sample. So in this case, your postal code is the cluster of individuals in the population that are located near each other, hence it's cluster random sampling, and you randomly sample or randomly choose which one of those postal codes is going to be included in your sample. Can't do the whole country, that would be way too much, so you just choose a subsection of ones that you're going to include. Excuse me. So this is also one that I wanted to include because it shows you that you can combine these techniques in a way that makes sense for the study that you're doing. So you're never restricted to just using a clustered random sample. You're never restricted to just using a stratified random sample. You can do what they did here and do a clustered and stratified random sample. So they did it clustered by choosing postal code sectors and randomly selecting those postal code sectors. And then within that, they used stratification by region, by population density, by the proportion of the population aged under 60, and the proportion of households with a head in a non-manual occupation. So these were characteristics that they thought would be associated with sexual behavior among people in that population. So they had some sort of theory or some sort of guidance that say, hey, you know what, this might be different by region. Right? Maybe in regions that are colder or get more rain, we'll see a different pattern of sexual behavior. This might change via population density, right? That might be a characteristic that affects sexual behavior. This might be affected by the proportion of the population that is under 60. And my favorite one is the proportion of households with a head in a non-manual occupation, because I just find it interesting that it might be that some people in manual occupations just come home and they are just too tired. And that might impact in terms of their sexual behavior. So these were characteristics that were identified. So what they would do is they would split these up by strata and they would identify regions. And then they would randomly select within those regions. They would split people up by region and then randomly select within those regions. They would split people up by population density. So the postal codes that they selected, they would select them based on population density, making sure that they have postal codes from low density, from mid density, from high density, stratified, and then also clustered. So you can combine these to get as representative a sample that gives you as tight a prediction as you possibly can by stacking these different techniques. So this was the study that kind of showed how they did this survey. And then when you have a survey that's done really, really well like this, you can then mine that data for tons of interesting insights. So this article that was published basically took a look at that NASTAL 3 study and compared it to NASTAL 2 and NASTAL 1. So NASTAL 3 was in 2012, NASTAL 2 was in 2000, NASTAL 1 was in 1991. And they looked at changes in the frequency of sex in Britain over time. And what they found was that the frequency of sex has declined recently in Britain, more markedly among those in early middle age and those who are married or cohabiting. So that is a surprising result, especially the married or cohabiting, and that it's declining. And this is something that you can infer because the NASTAL used proper sampling techniques and didn't look at all of Britain, but you are very confident in generalizing to all of Britain from that sample because it used the proper sampling techniques to choose its individuals. All right, so those are the different sampling techniques that we're going to take a look at. Any questions on that before we go to the next and final topic of the day? All right, so next we are going to take a look at inference scope, or scope of inference, however you want to say it. I've heard it both ways. So scope of inference basically are the rules and the techniques that you want to use, you want to think about to go from a sample and infer about a population. So these are just going to be the general principles. We're just going to introduce the general ideas of this, because in any research that you do, you are not interested in your sample. So if I study 50 individuals in a particular experiment, I'm not interested in those 50 individuals. I'm interested in the 5 billion individuals that they might represent in the population of humans. So you're not interested in the sample. You study the sample, but you're not interested in what happens in the sample. If we were, all we would need is descriptive statistics. All we would need is ways to make an elevator pitch about the 50 people that we, or individuals that we studied. That's not the case. We are interested in the population. And because of that, we need to use inferential statistics. And all inferential statistics are techniques for making inferences going from a sample to a population, so that we can do this intelligently, so we can do it in an unbiased way, so we can offload the procedure of doing this from our human mind, which has biases and does things incorrectly, to a more programmed, strict way of doing it, so that we can get an objective inference from sample to population. Now, we're going to get to those objective inferences in the second half of this course, but the general rule that you should take from today's class about inferring from a sample to a population is that it's only truly allowed when you have a random selection of individuals and they are taken from the population which the sample was selected. So you'll notice in that study that we just mentioned about the declining rates of sexual behavior, the title of that study did not say frequency of sexual behavior declining in general. It did not say frequency of sexual behavior declining in the world. What it said was frequency of sexual behavior declining in Britain, because it used data that was from a random selection of individuals, and those random selection of individuals were from the population of Britain. So they were very justified in saying, hey, what we find in this sample is going to apply to everybody in Britain. Very justified in doing that. However, once you go beyond the population where the sample was taken from, then you have to be very, 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 very cautious. And I'm going to show two examples of what I mean by this. And the one thing that I don't want to leave you with here, and this is why I'm showing two examples, I want you to be cautious when you're inferring from a sample to a population, but at the same time, I don't want you to ignore studies just because they might not fit exactly a particular population. So just because a sample doesn't fit a population does not mean that the study is not useful. And that's something that sometimes researchers get biased about. It's not that the study is not useful, it's that you need to be cautious. And we're going to see exactly what I mean on the second sample, or the second example. But let's start off with this first one. So this is extreme sample number one. And this was a study that was published about 13 years ago. So this is the title of the study: Improvements in Skeletal Muscle Strength and Cardiac Function Induced by Resveratrol During Exercise Training Contribute to Enhanced Exercise Performance. So that first key point, resveratrol, An antioxidant found in red wine has beneficial effects on cardiac and skeletal muscle function, similar to the effects of endurance exercise training. So this was a study that showed that this particular compound, resveratrol, which is found in red wine, had beneficial effects on cardiac and skeletal muscular functioning, and it's similar to endurance exercise training. This study was reported in the media. Does anybody remember the hoopla that came about when this was reported? Okay, so somehow media, the news, generalized, inferred from this report on a sample, they inferred that a glass of red wine is the equivalent to an hour at the gym, says new study. That was what was going around everywhere, with news anchors reporting this and saying, well, I guess I'm going to be working out tonight, maybe twice, because I'm going to reward myself. So this was making the rounds, and people, the worst thing that would happen with this is people saying, well, you know what? I always thought I needed to get more fit. I guess I'll just start drinking more red wine. It's like an hour at the gym, says new study. Or just imagine people who go to the gym and say, you know what? Going to the gym is really hard. I can drink a glass of wine like that. That's great, says new study. That's not what this new study says at all. But this is an example of improper inferring. This is an example of taking the scope of inference and stretching it to a breaking point where it no longer applies. So there are two reasons why this is incredibly wrong. I didn't even see this first line here. Love a good glass of vino, but hate hitting the gym to work it off. This news will make your day. No, it won't. All right, so it is 100% true. And this study provided evidence that resveratrol, an antioxidant found in red wine, no lie so far, has beneficial effects on cardiac and skeletal muscle functioning, similar to the effects of endurance and exercise training. Problem number one with this inference is that the subjects in this study were not given red wine. They were given resveratrol. So it's found in red wine. Tons of other things are found in red wine. So that's the first mistake, saying that, oh, we can generalize from just a compound to the entire delivery system of red wine. That was breaking the scope of inference, number one. The second thing, and I haven't shown this to you yet because I wanted this to sink in, just how ridiculous it was. The second thing is that the title of this is not improvements in skeletal muscle strength and cardiac functioning induced by resveratrol during exercise training contribute to enhanced exercise performance. That's not the title. There's a little bit more. It's that in rats, this was done on rats. So somehow the media thought, oh, wait a second, red wine, which was not used in this study, and the study was on rats, we're going to generalize to human beings taking red wine is as good as an hour of exercise. Resveratrol given to rats is as good for their muscle strength and cardiac function as them working out and doing endurance and exercise training. That's what you can generalize from this. In no way are you allowed, with that scope of inference, to go from resveratrol in rats to I'm going to get totally buff by drinking a glass of wine every single night. All right. Now that I said that, the one thing that oftentimes occurs when people first learn about this, and it kind of sticks with them for a while, is that they almost use this scope of inference idea as like a shield and basically deflect like any inference that's coming at them. So it would be like, oh, I found this new study and it's on, it's on memory. And it's like, well, what's the sample? It's like, oh, it's university students. Like, ting, I'm not going to infer from that. That's only university students. Or I have this other sample, but it was only done on people in India. It's like, ting, I'm not going to generalize from that because of the scope of inference. You want to be sure that you're aware of it. You want to be sure that you're cautious, but you don't want to throw out research that is done on other samples. You just don't want to do crazy generalizations like this. And I'll show you what I mean, because I don't want you to throw out the baby with the bathwater. So we're going to go to extreme example number 2. And when I saw this, this really makes me want to do another animal study, but online. This is what I would hope it would be like. just dogs sitting in front of their laptop answering my, telling me what my pictures look like. If only. But we're going to talk about a study that was done back in 1967. And this is failure to escape traumatic shock, done by Seligman and Meyer. And you might have heard about this study in your Intro to Psychology course. It's a very, very famous study. And the first thing I want to mention is that this is dogs. So this was a study that was done on dogs. And what they did is they shocked these dogs. I'm about to lose my voice here. They shocked dogs and they placed them in 3 different conditions. And the key difference was they could press a panel in order to escape the shock. That was one condition. Or anything they did wouldn't allow them to escape the shock. So they got shocked equal amounts of time, equal amounts of shock. But one of them could press a panel and stop the shock. The other group could press that panel, but nothing happened. They were just shocked in equal amounts. Then what they did is they had a second stage to this experiment where they tried to teach them another escape behavior in a different situation. So they said, all right, that was situation number 1. They took them to a new situation, and now all of the dogs could escape the shock. They were all capable of jumping over to a safe area in the shuttle box and escaping the shock in that manner. What they found was that the dogs that were in the inescapable shock condition in the first part of the experiment did not learn the escape response in the second part of the experiment. So even though they could escape, now their previous learning that they were unable to escape the shock interfered with their learning of being able to escape the shock. So these results were interpreted as supporting a learned helplessness explanation of interference with escape responding. Subjects failed to escape shock in a shuttle box, following inescapable shock in the harness because they had learned that shock termination was independent of responding. Also notice, I did not say S's, I said subjects. So again, get into that habit of just automatically saying those things in your mind. So that was the results of this study. And here, Seligman and Meyer were generalizing from dogs, from a sample of dogs, to all dogs, right? That's what they were saying in here. They were saying, well, these dogs had learned helplessness, so all dogs put in this situation would have learned helplessness, and they are able to do that. So that was 1967. We're going to fast forward to 1972. And Seligman wrote a paper called Learned Helplessness. And he writes, such uncontrollable events, so talking about the previous study, such uncontrollable events can significantly debilitate organisms. They produce passivity in the face of trauma, inability to learn that responding is effective, and emotional stress in animals, and possibly depression in man. So it took 5 years of research and multiple studies to go from we have a sample of dogs and we're going to generalize to all dogs to we have a sample of dogs and we have a sample of other animals. And now we're going to entertain the possibility that maybe this could also explain depression in man. So it's not that you take a look at the old studies and say, well, that has nothing to do with people because those are dogs and we can't generalize from the dogs to a population. That's true, you can't generalize, but that doesn't mean that there's nothing there. And it doesn't mean that you should ignore it. And it doesn't mean that even though it's beyond the scope of inference to go from dog to man with that one study, it does not mean that eventually you're not going to make it there. And in fact, Seligman did make it there. And in 1990, he published Learned Optimism, How to Change Your Mind and Your Life. And this was 100% based off of the research that came from that 1967 study on dogs. So eventually dogs generalized beyond just the population of dogs. Dogs generalized to other animals and other animals generalized to humans. And just to kind of give you a personal stamp of approval on this, this was literally the book that my therapist handed to me when I was being treated for depression and basically said, we're going to do this. And I tell you, every time I read that Seligman paper. I get a little choked up. I don't know if you can hear it in my voice right now. I want to buy those dogs steaks for the rest of their lives. But it's very, very important. If somebody said, those are dogs, they don't generalize to anything but dogs, and that was it, then I would still be in the depths of, dealing with my depression. But because somebody said, hey, you know what? Let's not just willy-nilly generalize. Let's not just say that people who suffer from depression were suffering inescapable shocks when they were children. That's not something that you want to generalize. You don't want to be the news report that is drinking wine to try to get buff, but you definitely don't want to just excuse it. And you definitely don't want to just dismiss it because it doesn't fit with what you can infer from a particular sample. So again, the general rule is you're only allowed inference when you take a random sample of individuals from that population that the sample was selected. But again, that doesn't mean that you dismiss anything that's not dealing with the population that you're interested in. It could be that you have gold in those findings, but you want to make sure that you're doing it intelligently and that you're making your inferences in a step-by-step manner. So instead of just reading a result from a study and putting it on the nightly news and breaking the limits of that scope of inference, you want to do your study, do some follow-up studies, get closer and closer to the population that you're interested in until you can finally make that inference in an intelligent way. All right, any final questions on that before we wrap up for the day? All right, so that is it for today's class. And next time we are going to start up on, what was I working on? We are going to start up on more statistics. Definitely, we're going to be doing more statistics. And it'll be a surprise for both you and me when we meet there next time. But other than that, we are done for today.